I want to run through a couple of the special cases on this section. The first thing, I'm going to kind of go out of order, but I've kind of got a reason I'm going in this order. I'm going to do them in 25. You've got an E equation. And really, if you're going to stick to the solve for t and then substitute idea, you have to go to logarithms. There's a lot of logarithm rules you have to work through, and it gets pretty complicated. It can be done, but it just gets complicated. So I'm going to show you a little shortcut that works really well for these problems that involve E. And then I want to show you some of the conic parametric equations as well. So let's run through this. And the way you really want to go with this type of problem, rather than solving for t, since they both have e to the t, just with some other stuff added in, get the first one solved for just purely e to the power of t. So let's kind of work through how that'll go. That'll be x equals 1 over e to the t, which means I would multiply both sides by e to the t. And I'll go ahead and take that step, I suppose. So eventually I get to e to the t power equals 1 over x. So we'll do a little dotted circle around it because it's not the final answer, but it is the kind of conclusion I'm looking for right now. So now, rather than try to solve for t with a logarithm again, I'm just going to take e to the t and get it in here. Now I've got to do a little bit of work with y as well. E to the t would be cubed, and that would be the exact same thing as e to the 3t, because if the power gets raised to a power, the powers multiply, which is the same thing as 3 to the t, or 3t, sorry. So now, since I've got e to the t isolated, and I know it equals 1 over x, then I'm going to have 1 over x cubed. So conclusion, y is 1 over x cubed. There's a little bit more because they do ask about the domain on this problem, and they do want to see a graph. So 1 over x cubed So let's look at the domain for a second, and I think the easiest way to think about that is concentrate on x, because typically for a function, x determines your domain, or x is the domain. I want to look at this x equation, but I want to back up to the parameter t. What happens as time goes backwards forever, which is kind of weird, but theoretically possible. What happens as time goes forward forever? So rather than look for x approaching negative infinity and positive infinity, we'll do the same thing for t. And now I'm going to figure out what x does there. So it's sort of like a two-part domain deal here. You got to look at t first, see what it does, then look at x later and see how it affects the end result. So let's see what happens as t approaches negative infinity and positive infinity, see how it affects x. So as t is going toward negative infinity, all right, well that would now become e to the negative t on the bottom, or maybe even backing up to here. If you put a negative infinity right there, that becomes e to the positive infinity. It just gets huge, so it goes to infinity. Now that's as time is going theoretically backwards. As time moves forward, all right, well, if we put in infinity right here, that becomes really huge on the denominator. So 1 divided by a really huge number is getting close to 0. So as time moves forward, we're getting really close to 0 on the x. So what we're doing is x, if time moves from left to right, negative infinity to positive infinity, x is actually going from infinity back towards 0. And 0 seems to be the limit. You'll never go past that. So when you graph this thing, and I'm just going to do a really rough sketch of 1 over x cubed. It's going to be sort of one of those kind of shapes. And I'm just going to do the part that's from x, or sorry, where x is from 0 to infinity. You could mess around with y if you needed to. You could extend this part to what's y doing. I don't think it's really too necessary for this graph. If I asked you to do this completely by hand, of course, you could just plug in some values. If you put in 0 for x, then you're going to get undefined. That's an asymptote. Put in 1 for x, you get 1. So 1 1's on here. Put in 2, you get 1/8, and so on. So again, x is going from the right to the left towards 0. So we are going to look something like this. And it might be good to put an asymptote in there to show that you know you're never quite going to make it to 0. So that's what your graph's going to look like. And really, when I talk about the domain, that's what I really need to see right there. All right, we'll talk about 23. I'm kind of going out of order, but I want to put these conics together. When you have parametric equations and you have trig values in there, they're generally going to produce a conic section. Definitely the ones you're going to see in our book. So, if you don't know, you might eventually figure out what these things are. I can look at that and tell you it's an ellipse, and probably by the end of this section you'll be able to do the same. But we can kind of play around with this thing and kind of figure out what to do. It really kind of all goes back to the fact that a cone is round. It all goes back to the fact that a cone is round. All right, it's really a triangle mixed with a circle in 3 dimensions. But because it's round, the cone is always governed by your circle equation. X squared plus y squared equals r squared. And we've got some trig definitions that go along with that, and they refer back to the unit circle because your x values always revolve around cosine, y values always around sine, and for the unit circle it always equals 1. And this also brings back into play how your standard forms of ellipses and hyperbolas come in, so all that good stuff. But for now, I just want to focus on this aspect, that because the cone is circular, these come from the cone shape, we can use this true definition of a circle and go up to our trig definition for a circle. So looking at that, I've got a cosine here, I've got a sine here. I don't necessarily want to solve for the parameter. Now, it's possible. I'm not going to tell you it's wrong. You can certainly solve for theta, plug it back in. If you try it, you'll probably regret it pretty quick. It gets pretty complicated, and you'll really probably prefer this. I know I do. So what I'm going to do is I'm going to aim for this identity right here, and I'm going to solve for cosine, and I'm going to solve for sine. So for x, or for the x equation, I just need to divide by 2. And I've got cosine the theta by itself. For y, I just need to divide by 3, and I've got sine by itself. Okay. Now if I'm going to the trig form over here, cosine needs to be squared. So if I square that, I get x squared over 4. Sine also needs to be squared, so that becomes y squared over 9. And should start looking pretty familiar. So when I told you that I could glance at that and tell it was an ellipse, now at this point, you also should be able to see it's definitely an ellipse if you couldn't tell before. So now we've got the general equation for an ellipse, or standard form for a function at least. The center there would be at 0, 0. We're going to go 2 in the x direction. We're going to go 3 in the y. Put some vertices on there. And there is our ellipse. Now direction does matter, so we do need to look into that. What I'm going to do, I need to look at the angles. And I'm going to try 0 because that's easy. I'll start with some easy ones like pi over 2 and pi and see if that's enough to figure it out. Hopefully it will be. Sometimes if you start seeing some undefined values, when you start doing tangent, secant, cosecant, those kind of things, you may have to go a little more detailed, like maybe instead of every quarter circle, go like 0, pi over 6, pi over 4, pi over 3, things like that. We'll see what happens with this. I think this is going to do it. So I want to see what x does when I plug in these different values. So let's come up to the x equation. When I put in 0 for cosine, or for the angle, cosine of 0 is 1, so that's going to be 2 for x. So I'm definitely starting right there. That's something to go by. All right, put pi over 2 in for your angle, you get 0. So when you get to pi over 2, you're at 0 for x. So that's maybe sort of helpful, but I don't really know which way I'm going yet. I'm definitely starting here. I'm either going that way or that way, but it's not the most helpful. And now I'm kind of thinking if I really even need pi down there, because when I put in pi, it's -1, so it's -2. That's probably not super helpful, so I really don't know. I'm starting here, and I'm either going that way or that way. So I need to narrow it down some more. So let's see what y is doing. And when I said I probably didn't need the third one, I think 2 is going to probably do it. So we'll get a couple y values. If we need to do a third one, we will. But I think we're going to get it by the time we do a couple of these. I'm pretty confident y is going to be 0 there, but I guess I should probably check. I mean, really, when x is 2, you pretty much got to be 0 for y. It's the only value possible in the graph. But let's double check. Put in 0 for angle. Sine of 0 is 0, so yeah, that is 0. This will be the thing. If we go up, we're going this way. If we go down, we're going that way. So we put in pi over 2 for sine, and that's going to be 1. So 3 times 1 is 3. So we're going from 2, 0 to 0, 3. We are going this way. So now we've got the direction this thing's rotating through. And really, there's no limit to what your angle can be. As your angle's getting bigger and bigger, this thing's rotating counterclockwise. And I probably wouldn't ask you about domain on this one because it's just from -2 to 2, and range is -3 to 3. Really what I do want to make sure you can handle is getting this direction of rotation. Because when we start graphing things that are moving, that's important. We want to make sure it's moving in the right direction. All right, 31 is related to this, pretty close. It is a conic because it's got some trig values. It's a little trickier though. So I'm going to go back to that same idea. We're dealing with a cone. A cone is circular. We can use our circle equation. And I'm going to start with the trig form of that. Cosine squared plus sine squared equals 1. Should be a theta in there, but we'll be all right. We know that. And I want to use one of the identities. There's a couple other identities that come from this. I want to use one that's got tangent in it. And hopefully secant shows up too. And to make that happen, you can divide by cosine everywhere. I'm dividing both sides, the entire side by cosine, but I'm just going to write it everywhere to make it easier. I know that's going to produce a tangent, which is what I want. So that's 1 plus tangent squared theta over secant squared theta. Or not over, just equal to. And that's exactly what I'm going for here, because I do want tangent and secant to show up. Now we can use that same strategy. If I were to divide by 4, then that would be secant. If I were to divide by 2 for y, that would be a tangent. So, putting it in here, the main equation, 1 plus tangent squared, so that needs to be squared, y squared over 4, is equal to secant squared, so I need to square both of those, x squared over 16. All right, now, that's looking very similar to a hyperbola. If I get this thing equal to 1, that would mean subtracting the y. So that is now our standard form for a hyperbola. The book doesn't ask for direction on this, and I was going to put it in here just to do it. It gets pretty complicated on the hyperbola because it's technically not even a function. So the book didn't ask for direction of rotation. And I decided that I'll let you know I'm not going to put that on the quiz for a hyperbola, so we'll just get the graph, make sure to remember how to graph a hyperbola, and then we'll be done. So centers at 0, 0. We are going 4 to the left and right, and that's because of the a value, which is the a value goes with the positive, either x squared or y squared is positive, in this case it's x. So it's opening left to right, those are my vertices. From those vertices, I go up and down 2, which is the square root of 4, and make my box, connect my dots, that's my asymptote, or my set of asymptotes, and there is our hyperbola.